two pieces of code. Same task. Add up a million numbers. On the left, a loop. Go through them one at a time. On the right, a single line. Watch. The loop crawls, and before it's even warmed up, the right side is already done. Same answer. Same computer. Roughly 100 times faster. The right side is doing something the left side can't even see. And that hidden something is the whole point of this video. Because the gap between a beginner and a real data scientist isn't how much Python they know. It's whether they still think one item at a time or whether they've learned to operate on everything at once. By the end of this, you won't be able to unsee it. Quick question first. Why Python at all? It's not the fastest language, far from it. But here's the trick that makes it the language of data science. You write slow, friendly, readable Python, and underneath, the heavy number crunching is handed off to blisteringly fast code written in C. You orchestrate. C does the lifting. Python is the comfortable cockpit on top of a very fast engine. So here's our journey. We'll start with just enough core Python to be dangerous. Then we'll meet the two libraries that the entire field runs on, numpy and Pandas, and the one mental shift that ties them together. Not a syntax store, a way of thinking. Let's build it. Chapter 1. The basics, and one picture to hold on to. Let's clear up the most basic thing, because almost everyone pictures it wrong. When you write x equals 5, people imagine a box labeled x with a 5 inside it. That's not what Python does. The 5 is an object sitting in memory, and the name x is just a sticky label pointing at it. The name isn't a box. It's a tag. Why does that matter? Because two names can tag the very same object. Say b equals a, and now a and b are two labels on one single thing, not two copies. Change that thing through one name, and the other name sees the change too, because they were never separate. Hold that idea. In about 20 minutes, it's going to explain a bug that haunts every beginner. Now scale that picture up because this is the image the whole video hangs on. A list of a million numbers in plain Python is a million separate objects, each one boxed, wrapped in overhead, scattered all across memory, each with a little tag pointing at it. A million tiny boxes strewn everywhere. Remember the slow loop from the start? That picture is exactly why it was slow. Keep it in mind. One more nicety. Python is dynamically typed. The tag doesn't care what it points at. The same name can hold a number now, a word later. The core types you live in are simple. Whole numbers, decimals, text strings, and true or false booleans. And to drop a value neatly into a string, you use an F string, the modern, readable way to build text. That's the vocabulary. Let's start combining it. There's one fork that trips people. Some things can be changed in place, some can't. A list you can edit, add, remove, overwrite. A number or a string, you can't. You only ever make a new one. This matters the moment two names tag the same changeable object, edit it through one, and the other quietly changes too. That's not a Python quirk to fear. It's the direct consequence of names being tags, not boxes. Text is data too, and strings are sequences you slice just like lists. The real workhorses are the cleaning methods. Strip the white space, lowercase it, split on commas, replace the junk. Honestly, 90% of messy real-world data is text that needs exactly these moves before anything else can touch it. Chapter 2. Functions, your verbs. A function is just a named, reusable block of behavior. Data goes in, a result comes out. You define it once with definite, give it inputs, its parameters, and it hands back a value with return. Instead of copy-pasting the same 10 lines everywhere, you write them once and call them by name. Functions are how you stop repeating yourself. A couple of conveniences you'll see constantly. Arguments can have defaults, so you only pass what differs from the usual case. And you can pass them by name, which makes a call read like a sentence. There's also a way to accept any number of arguments. You'll recognize it as star args. But don't sweat it early. You'll reach for it far less than you'd think. Two ideas here actually matter a lot downstream. First, a lambda, a tiny throwaway function written in a single line, for when naming it would be overkill. And second, the big one, in Python, a function is itself an object. You can hand a function to another function, like passing a recipe instead of a cooked meal. Hold that. It's exactly how the data libraries let you say apply this operation to everything. Chapter 3. The 4 containers. Most of your data lives in containers, and there are 4 worth knowing cold. The first is the list, an ordered, numbered sequence you can change freely. Square brackets, items in a row. You reach in by position, and Python counts from 0. So the first item is index 0. The list is your default bag for a bunch of things in order. To list moves, you'll use every single day. Slicing, grab a range with a colon, like items 2 through 5, in one stroke. And mutation, append to the end. Remove, overwrite a slot. A quiet warning we'll return to. Slicing and copying are not the same thing, and confusing them is a classic source of mystery bugs. Next, the tuple. Think of it as a list that's been frozen. Same idea, round brackets, but you cannot change it once it's made. Why want that? Because fixed things are safe and predictable. A coordinate pair, a row of a table, a value you want to guarantee nobody edits by accident. And only frozen things are allowed to be dictionary keys, which is the perfect cue for the most important container of them all. The dictionary. If you remember one container, make it this one. A dict stores pairs, a key, and the value it maps to. Names to phone numbers, a user ID to their record. You don't look things up by position. You look them up by key. It is, by a wide margin, the workhorse of data work. Now here's a question. Actually pause on it. You've got a million names, and you need to check is this one in there, 1,000 times over. In a list, each check means scanning, potentially the whole million. In a dict or a set, each check is basically instant, no matter how big it gets. That word, instant regardless of size, has a name, order 1. Remember it. It is the single most important word in the algorithms video, and it comes back with a vengeance. Which brings us to the set. Like a dict, but keys only, no values. It does two things brilliantly. It throws away duplicates automatically, hand it a messy list, get back the unique items. And it answers is this in here instantly. Deduplicating, membership tests, removing repeats. Reach for a set, and a slow scan becomes a snap. Here's the single most common thing you'll do with a dict. Count. How many of each class? How many times each word appears? You walk the data once and tally into a dict, each key to a running count. It's so common that Python ships a ready-made counter for it. Counting is the quiet backbone of an enormous amount of data work. So a quick map to carry. Ordered things you'll edit, a list. Fixed things you won't, a tuple. Lookups by key, a dict. Unique items and fast membership, a set. Pick the wrong one, and your code is slow and clumsy. Pick the right one, and it's fast and obvious. Choosing the container is half of writing good Python. Chapter 4. Doing things and a twist. Control flow is how code makes decisions, and if statement runs a block only when a condition is true, with elif and else for the other cases. That's the branching. Fork the road depending on the data. There's not much to it, and Python keeps it clean by using indentation, not curly braces, to show what's inside the branch. And then the loop. The for loop walks through a container, one item at a time, doing something to each. This is the bread and butter of every beginner. But notice the phrase I just used. One item at a time. That's you personally, instructing Python to handle each element by hand. Keep an eye on that phrase. It's about to become the villain. Two tiny loop helpers you'll use constantly. Enumerate when you need the position and the item together instead of a clumsy manual counter, and zip to walk to lists side by side, pairing them up. They make loops read cleanly. Though, as you're about to be reminded, the real goal is to write fewer loops, not prettier ones. Python has a gorgeous shorthand for the most common loop, building a new list from an old one. Instead of 3 lines with an append, you write it in one. This expression, for each item, optionally where some condition holds. It's called a comprehension, and once it clicks, you'll write them everywhere. It reads almost like English. The squares of the numbers that are even, and it's not just for lists. The same one-line pattern builds dictionaries and sets too. A dict comprehension, a set comprehension. It is genuinely one of the most Pythonic things you can learn, and it makes data shuffling code short and readable. You feel clever writing them, which is exactly why the next 30 seconds sting a little. Here's the catch. A comprehension is beautiful, but under the hood, it is still a loop. It still walks a million items one at a time, in Python, with all that per item overhead. You wrote a slicker loop. You did not write a faster one. The fast lane, the thing the right side of our opening was using, is still completely empty. So let's finally walk into it. Chapter 5. Why arrays are fast. Meet the numpy array, and meet the most important object in all of data science. On the surface, it looks like a list of numbers. Underneath, it is something completely different. A single, solid, contiguous block of memory, all of one type, packed end to end. Not a million scattered boxes. One unbroken bar. That difference is everything. So let's finally answer the question from the very start. Same million numbers, same processor. The plain Python loop is 100 times slower. Where does all that time actually go? Take a second and guess, because the answer rewires how you write code. It is not that Python's addition is slow. It's everything happening around the addition. Here's the slow lane laid bare. For each number, Python has to find the boxed object, unwrap it, check its type, do the add, rewrap the result, and chase a pointer to the next box somewhere else in memory. The actual addition is a rounding error. The overhead and the scattered memory chase are the whole cost. A million times over. That is why the loop crawled. Now the fast lane. Because a numpy array is one contiguous block of one type. There's nothing to unwrap and nothing to chase. numpy hands the entire block to a tight loop written in C, which rips straight through neighboring memory. And modern chips can even add several numbers in a single step. You stopped giving a million instructions. You gave one, all of it, at once. That move has a name, and it is the soul of this whole video, vectorization. You replace an explicit loop over items with a single operation on the whole array. You write less code, and it runs dramatically faster, because the looping drops out of slow Python and into fast C. From here on, the goal is simple. Stop touching items one at a time. Chapter 6. Speaking in arrays. So what does thinking in arrays actually look like? You operate on the whole thing at once. Array times 2 doubles every element. Array plus array adds them slot by slot. Take the square root of an array, and you get the square root of every entry, in one stroke. The loop hasn't disappeared. It's just no longer in your code. It moved down into C, where it belongs. And where do arrays even come from? You rarely type them out. You generate them. A range of evenly spaced numbers, a grid of zeros to fill in, ones, or random values to simulate data. One short line conjures a million-element array, ready to compute on. Creating the data is every bit as vectorized as using it. Now the idea that makes arrays feel like magic. Broadcasting. Think of scaling a recipe. You have amounts for one person, you want to serve 4. So you multiply every ingredient by 4. You don't write 4 next to each line. One number stretches across all of them. That's broadcasting. A smaller shape automatically stretched to meet a larger one, so the operation just works. Let's test it. Predict with me. A row of 4 prices plus a single tax number. That stretches the one number across all 4, and it works. But a table, 4 rows by 3 columns, plus a row of just 3 numbers. Does that work or blow up? It works. The row stretches down every row of the table. The rule is simply that the shapes have to line up. And when they do, no loops, no copies, just the result. Here's a move you'll use hourly. Boolean masking. Compare a whole array to something, array greater than 0, and you get back an array of true-false answers, 1 per element. Feed that mask back in, and you pull out exactly the elements where it's true. No loop, no if statement. You ask a question of the entire array, and it hands you the matching values. Filtering becomes a single expression. You can also index with a list of positions. Give me elements 0, 5, and 99, and grab them all at once. Combine that with masks, and you can select, replace, and rearrange data in sweeping single strokes. Where you set the value can be a question, not a position. Set every negative number to 0. One line, whole array, done. Last piece. Arrays have shape, and operations have direction. A two-dimensional array is a grid, rows and columns. When you sum it, you choose an axis. Collapse down the rows to get a total per column, or across the columns to get a total per row. That one idea, which direction do I collapse, is the seed of the next chapter, where the grid becomes a real table of data. An array shape is something you reshape at will. The same numbers, rearranged into a different grid. Flatten an image into one long vector. Fold a flat list back into rows and columns. Models are famously picky about the exact shape of what you feed them, so reshaping and watching the dimensions line up quickly becomes a daily reflex. Chapter 7. Pandas, Arrays Grow Up. numpy gives you fast grids of numbers. But real data is messy. Named columns, mixed types, dates, missing values. That's Pandas. Its star is the data frame. Think of a spreadsheet you can program. Rows, labeled columns, and underneath each column is a numpy array. So you get the speed of arrays with the convenience of a real table. Pandas is where most data scientists spend most of their day. First, getting at your data. Grab a column by name, and you get a series. A single column with an index. To pull out rows and columns together, you use two tools. LOC, which selects by label, and iloc, which selects by position. That split confuses people for a week and then becomes second nature. Names with LOC, numbers with iloc. Now watch a familiar face return. To filter a table, say, all customers older than 30. You write df, square brackets, df.age greater than 30. That inner part builds a true-false mask over the whole column, exactly like numpy. And the table hands you back only the rows where it's true. The masking idea you just learned scales straight up from arrays to entire tables. The very first thing you do with a fresh dataset is simply look at it. And Pandas makes that one-liners. Describe hands you the count, the average, and the spread of every numeric column at a glance. Value counts tallies how often each category shows up. Before any modeling at all, this is how you build a feel for what you're actually holding. Here's the most powerful pattern in all of data analysis. Group by. Say you want average sales per region. You split the table into groups, one per region. You apply a calculation to each group, the average, and you combine the answers back into a tidy result. Split, apply, combine. 3 words. It answers a staggering fraction of the questions you'll ever ask of data. Burn that shape. Split, apply, combine into your memory, and here's why. It is not a Pandas trick. It is a way of thinking that you are about to meet again, almost word for word, in the SQL video under the name group by. Same idea, different language. Learn it once here, and you'll get it there for free. These tools are more alike than anyone tells you. Real data is rarely in one table. Customers in one, orders in another. Merge joins them on a shared key, match each order to its customer, and stitches them into a single table you can analyze. If that sounds a lot like a database join, hold that thought. It is exactly the join from the SQL video, and we'll go deep on it there. Same operation, two homes. Sorting answers the top and bottom questions that fill every report. Sort values orders the table by any column. And for the classic, which are the top 10, there's a direct call that beats sorting the entire thing. Leaderboards, biggest movers, worst offenders. It's the same one move, over and over again. Missing data is everywhere, and Pandas marks it with a special value. NaN, not a number. Three things will bite you if you don't know them. NaN is not equal to anything, not even itself. A single NaN turns a whole column of integers into decimals, and most calculations quietly skip it. An average ignores the missing entries rather than failing. Know those three, and missing data stops being a mystery. Here's a quiet performance lever most beginners miss. Every column has a type. It's D-type. Numbers stored as compact integers fly. Text stored as generic objects crawls and hogs memory. Convert a low-variety text column into a category, downcast oversized numbers, and a sluggish, bloated data frame can shrink and speed up dramatically without changing a single value inside it. To stack tables, this month's rows under last month's, you concatenate. But here's a trap that bites everyone, and it's a direct teaser for the algorithms video. Never grow a data frame or an array by appending inside a loop. Each append quietly copies the whole thing, and your code silently slides from fast to painfully slow. Build a plain list, then convert it once at the very end. Now the bug I promised you 20 minutes ago. Remember, names are tags, and two tags can share one object. A slice of a data frame can be a view, a second tag onto the same memory. So when you filter and then assign in one chain step, you might be writing to a throwaway copy, and your real table never changes. Pandas even warns you about it. The fix is to be explicit. Select with LOC in one shot or take a real copy. That one picture from chapter 1 just saved you hours of confusion. One last trap, and it's the theme of the whole video in miniature. Pandas has a method called apply, and beginners reach for it to run a function over every row. It looks tidy. But predict it. Is apply fast? It's not. Apply is a Python loop in disguise. One item at a time, all that overhead, the slow lane again. Whenever you can, phrase it as a whole column operation instead. Reaching for apply by reflex is the most common way people accidentally write slow pandas. Chapter 8. Lazy data, iterators and generators. Quietly, every for loop in Python leans on one idea. The iterator, an object that just knows how to hand you the next item, on demand, until it runs out. You don't usually see it, but it's the engine under the loop. And once you can produce items on demand, a powerful door opens. You don't have to build everything up front. That door is the generator. Instead of computing a whole list and holding it in memory, a generator produces values one at a time, only when asked, using the keyword yield. It's the difference between cooking the entire buffet before anyone arrives versus cooking each dish to order. The work is the same. The memory it ties up is wildly different. Why should a data scientist care? Because your data set often does not fit in memory. You cannot load 100 gigabytes of images at once. So the data loader that feeds a neural network is a generator, streaming the next batch just in time, training stage after stage without ever holding it all. Lazy isn't a flaw here. Lazy is how you work with data bigger than your machine. Chapter 9. Objects. And one idea, 10 times. Time to name something you've been using all along. In Python, everything is an object, a bundle of data together with the actions that belong to it. A string isn't just text. It carries methods, like make me uppercase, attached right to it. Data plus the things it can do, packaged together. That's the whole idea of object-oriented programming, and you've been swimming in it since line 1. You can define your own with a class, your own custom type, holding some state and offering some methods. Early on, you'll use far more classes than you write, so we won't dwell on the syntax. The point is the shape. An object remembers things about itself and exposes a few buttons that act on what it remembers. And here is where it pays off for you specifically. In machine learning, a model is an object. You create it, you call model.fit to train it, and now the object holds everything it learned. Then you call model.predict to use it. The trained knowledge lives inside the object. Fit and predict are just the buttons on the outside. That little pattern is the entire interface of scikit-learn. Now step back and see the gift hiding here. df.groupb, model.fit, tensor.backward. Every library you will ever touch is the same shape. An object that holds some state, a handful of methods you call, and fast C or CUDA doing the real work underneath while you orchestrate from comfortable Python. You are not learning 10 libraries. You are learning one idea, 10 times. Once you see it, every new library is just new vocabulary on a grammar you already know. Chapter 10. The real workflow. So how does an actual project flow? Almost always the same 4 stages. Load the data, usually read CSV, straight into a data frame. Clean it. Handle the missing values. Fix the types. Transform it. Build the features your model will learn from. Then model. Most of the real work and most of your time lives in the middle too. The glamorous part is the smallest part. And nearly every step is the tools you just met working together. Filter rows with a Boolean mask. Summarize with group by. Split, apply, combine. Stitch tables with merge. Fill the gaps in the missing data. None of it is exotic. It's the same small handful of moves composed. Data science is mostly fluent, confident data wrangling, and you now know the grammar of it. And you'll want to see your data, not just compute on it. A single line with matplotlib or seaborn turns a column into a histogram, a scatter, a trend. A picture instantly catches the outlier, the skew, the broken assumption that a table of numbers quietly hides. Plotting isn't decoration in data science. It's how you catch the problem before it ever reaches your model. And the golden rule threads through all of it. Do not loop when you can vectorize. If you catch yourself writing a for loop over rows, stop and ask, is there a whole column way to say this? Almost always, there is. That single habit is the difference between a script that finishes in a blink and one you leave running overnight. It is the through line of everything we've done. And one last professional reflex. Measure before you optimize. Python's timing tools tell you exactly which line is slow. And 9 times out of 10, it's a hidden loop you can vectorize away. Don't ever guess at performance. Measure it, fix the one real bottleneck, and ignore the rest. Most of your code is already fast enough. The skill is finding the part that isn't. One small professional habit that saves real pain. Reproducibility. Anything random. Shuffling data, splitting into train and test, initializing a model should be pinned with a random seed, so you get the exact same result every run. Without it, your numbers wander and you can never tell what changed. With it, your work is something another person, including future you, can actually trust and repeat. And what can you happily ignore for now? Web frameworks, async, the deep magic of meta-classes. None of it is on the path to doing data science. Learn just in time. Build something real and pick up each piece exactly when a problem demands it. You don't need all of Python. You need this slice and the instinct to operate on everything at once. So here's the whole journey on one breath. A name is a tag, so plain Python data is scattered and slow. A numpy array is one solid block, so it's fast. And vectorizing means operating on all of it at once, instead of one item at a time. Pandas brings that speed to real tables. Split apply combine answers your questions, and every library you'll meet is the same object with methods you already understand. That's the toolkit. Let's end where we began. That loop, racing the one-liner, losing by a mile. At the start, you couldn't see why. Now you can. The loop is touching a million scattered boxes, one tag at a time. The one-liner hands a single contiguous block to C and says, all of it at once. You came in writing the loop. You leave writing the line. Not because someone told you to, but because you can finally see what it's doing. Everything else, Pandas, PyTorch, the whole stack, is just this one idea scaled up. So stop looping and start thinking in arrays. Do that, and Python stops being a pile of syntax and becomes what it really is, a comfortable handle on an enormously powerful engine. Subscribe for more such intuitive videos.